Welcome everybody joining us on our second webinar of 2025. And in this session, we are going to be going back to some basics and covering all the fundamentals that you need to know to build a great Wi-Fi network. So really looking forward to this one, stripping back, going back to those building blocks of what we need to know so that we can then build a awesome Wi-Fi network. And Dale, maybe you can just do some introductions for us.
Yes, absolutely. So today we have a very special guest, a remarkable man. Especially in the world of Wi-Fi, wears many hats. We have Francois Verges, owner and managing director of Simfio Networks. How are you today, Francois?
I'm very good, Dale. Thank you for having me, and it's a pleasure for me to be able to chat with you guys and talk about Wi-Fi. As always, I love Wi-Fi, so I love talking about Wi-Fi.
Yeah, glad to have you here with us. Then we have Matt Starling, Ekahau Senior Director, Product Marketing and ECSE. Then we have Wireless Stu, aka Sidekick Stu Gomez, Global Director of Community and Customer Engagement, and myself, Dale Tyler, Sales Engineer for the Americas with Ekahau. And with that, back to you, Matt.
Thank you, Dale. And what I've got running here, I've got my Sidekick 2 down here connected to the Ekahau Analyzer application. And I really wanted to understand, not only is the Wi-Fi good here, but also what is the backhaul speeds like? Because having great Wi-Fi is one thing, but if you've not got a great internet speeds, then it's not going to be good to do this kind of webinar. So I fired up my Analyzer application and I run a trusty speed test, and you can see in a second how the Wi-Fi looks. So the actual RF is pretty nice here. I'm using an 80 megahertz wide channel on 5 gigahertz, and the actual backhaul speeds for the download is pretty good. So when I did this earlier, I got around 75 megs. I think it might creep up to 70, 75. And then, yeah, so I could actually test to see how good the Wi-Fi is, but also how good is the backhaul. So yeah, I thought that'd be a nice little thing to quickly show so you can see what we prepared for you for today's webinar and using the Ekahau tools. Okay, the agenda for today, we're actually going to be giving away an ECSE design seat to one of you lucky webinar guests. So we'll be covering that shortly. We have lots of great RF fundamentals in terms of wavelength characteristics, amplitude, transmit power, how you should be configuring your radios, and we're going to also be giving lots of great tips and some nice live demos at the end from Francois. Before we actually jump into it though, if you've logged into Ekahau Cloud today, you might have noticed that AI Pro Online got an update and we have some new features available for you. So you can create your own custom attenuation objects now. You can draw in the warehouse racks, your cubicles, your pillars, whatever you would like to do. We've also improved our automatic wall detection on our PNG and JPEG files. So when you import a floor plan, we can actually detect the windows as well. And a few other things around the wall drawing stuff like the fixed length wall. So for doors, and a nice new feature there is actually you can import from your desktop application. If you built a file there, a predictive simulation model with your areas, your walls, your anything really, you can import that now into the AI Pro Online. So welcome to everybody that are brand new to the Ekahau webinar series. If this is your first time seeing and hearing us at Ekahau, might be wondering what we actually do. And we support you with the whole life cycle of the Wi-Fi network. So whether you've got to design or redesign a new Wi-Fi network, you can leverage Ekahau. If you've got an existing Wi-Fi network that maybe isn't quite performing how you would like it to be performing, you can use the Ekahau tools to optimize your existing Wi-Fi network. And also, we don't want to just have a great performing Wi-Fi network. We also want to make sure it's as secure as possible. So we try to make it as easy and as obvious and clear for you users when you do a survey or you do anything with Ekahau, to highlight to you any potential security vulnerabilities in terms of rogue access points, in terms of interferers you might have, or even if you've not configured your networks as securely as you possibly can. So that's what you can use Ekahau for. And we're really lucky today because we actually have Francois joining us, and Francois is one of our most distinguished Ekahau ECSE instructors. So ECSE is a industry recognized certification all around Wi-Fi. So we teach you how RF works, but also we teach you how to apply that practically with the tools. And we have 3 different 4-day instructor-led classes that can be delivered virtually or in person, and that goes from designing and troubleshooting to some really advanced stuff. If you want to jump in straight away, we have some self-paced video on demand training for you as well, which you can access to watch some videos to get you up to speed, which you can see across the bottom there. Okay, so how are we going to be giving away an ECSE design seat? You're going to just have to stay tuned until the end of the webinar to find out, I'm afraid. I know I really hate it when TV shows do that, like a little cliffhanger to make you like stay on and whatever, but you know, you want to win an ECSE design seat. We're going to tell you at the end how to do that. Okay, so actually I'm going to stop sharing now and hand over to Francois.
Yeah, let me take over. See that? Works? Okay. Hopefully people don't get tired of my French accent and leave the webinar before you give the seat away. I guess we'll see. I'll try my best. All right. Well, good morning, everyone. Good afternoon, depending on where you guys are. Good evening. Today, I'm just going to talk a little bit about Wi-Fi fundamentals. We have a few things that we've prepared for you. I'm not going to go too deep into the subjects. That one of the reasons why we do the Wi-Fi training, the ECSE design class, for instance, to go deeper into the Wi-Fi fundamentals. But I wanted to kind of cover a few important topics that you might find interesting. So we'll talk about Wi-Fi design. We'll talk about how Wi-Fi works a little bit, and then we'll do a little demo using the Ekahau tool to see how we can do Wi-Fi design, what's important to keep in mind when we do Wi-Fi design. And then we can talk about Wi-Fi optimization as well, and how we can use the Ekahau tools to optimize a network that we may already have running. So when we talk about Wi-Fi, usually, and we talk about Wi-Fi fundamentals, the first thing we talk about is the protocol itself, the evolution of the Wi-Fi protocol. And Wi-Fi is quite an interesting technology because it's not that old. It's about 25 years old, but it has evolved a lot, over the past 25 years. It's not like Ethernet where it's been the same and hasn't changed really in the last 20, 30 years. Wi-Fi is always improving itself. There's a lot of innovation around Wi-Fi, and we can also see that the technology has been adopted by a lot of people now. It's the main way of us accessing the network. And so you can see that right now in the journey of Wi-Fi, we are starting to use the 7th generation of Wi-Fi, Wi-Fi 7. And we start to see that as well in the enterprise space, where vendors now have their Wi-Fi 7 APs available, and we are deploying Wi-Fi 7. One thing that's interesting as well with the evolution of Wi-Fi is understand which frequency band we've been using with Wi-Fi. Originally, Wi-Fi was defined on the 2.4 gigahertz frequency band. Then the 5 gigahertz band became available, and we'll talk about why, but it became like the go-to frequency band for enterprise Wi-Fi because we could have better performance. And now that we have 6 gigahertz becoming available with Wi-Fi 6E and Wi-Fi 7, we are also seeing kind of a transition slowly but surely to 6 gigahertz because once again, we'll have better performance on that frequency band. So it's interesting to understand. And if you're just starting with Wi-Fi, that's one piece that you can start with is try to understand the different version of Wi-Fi, which one supports which frequency band, and that helps you to kind of understand where Wi-Fi is today. I know when I started to study Wi-Fi, it was the 802.11n days or 802.11ac days, and I pretty much went back, to the beginning to kind of understand how the protocol evolved, and that helped me to better understand, the Wi-Fi we use today. So one thing that we also like to understand when we talk about Wi-Fi is the radio frequency aspect of it. So Wi-Fi is the RF technology. If you look at the standards, it's actually specifying the layer 1 and layer 2 specification of the protocol. So layer 1 is important, and layer 1 can be a little different from what we're used to in the networking industry. So that's why we like to kind of better understand that RF piece. And one thing that we talk about when we talk about Wi-Fi and RF and the RF signal, the Wi-Fi signal, is on top of talking about frequency, we also talk about amplitude. And amplitude is pretty much the power. How much power is the signal carrying? And so here on this slide, you have two different signals. These signals have the same frequency, meaning they have the same number of cycles. But you can see that the amount of energy they're carrying is not the same. The one at the top is carrying less energy than the one at the bottom. So here we would say that the signal at the bottom is a stronger signal because it's carrying more energy and it has a stronger amplitude. Why do we care about amplitude in Wi-Fi? Well, we care about amplitude at different levels. We care about amplitude when we talk about the receiving signal. So in Wi-Fi, we talk a lot about signal strength, RSSI, received signal strength indicator, and this is pretty much the amplitude of the signal when the device is receiving that signal. So we want to make sure that that amplitude is high enough so that the Wi-Fi device receiving the signal can actually understand the Wi-Fi signal. So this is one piece where we'll talk about amplitude. And we also talk about amplitude when we actually transmit the signal. So in Wi-Fi, we call it transmit power. And the transmit power, it's pretty much, or sometimes we also talk about ERP, and we'll talk about that in a bit. But that pretty much, talking about the amplitude of the signal when we actually transmit the signal. So we'll transmit a signal will propagate in the space in our environment, and then we'll receive the signal on the client end. So we need to make sure that we have enough signal when we receive it, and then part of understanding the amplitude and how the signal will lose some of its amplitude as it travels from the transmitter to the receiver will help us understand all of this and make sure that we are designing a Wi-Fi network that works for everyone. A question that we get sometimes is how much power do we use? And this is usually related to the transmit power of our access points. How much power do I need to configure on my APs? Because we are limited in terms of transmit power by what the regulation allows us to do. But it's also usually not a best practice to use the maximum transmit power allowed by the regulators for a few reasons. And one of the main reasons is that you don't want to end up in a situation where your access points are just yelling out the signal so the clients can hear them really well, but then the clients do not have the same capability of talking back as loud, and then the AP doesn't have that same level of signal coming back and might not be able to hear the clients. So there's like a balance to find when we configure the transmit power of the access points. You'll see that in Ekahau by default they're using 14 dBm for 5 and 6 gigahertz and 8 dBm for 2.4. And then here on this slide, you can see that they are talking about transmit power. You can see it here, the 14 dBm. But they also talk about ERP. And the ERP will take into account the transmit power, but they will also take into account the gain of the access points or the gain of the client. And here you have an example where you have a positive gain of 3 dBi on the AP, which gives you an ERP of 14 plus 3, 14 dBm. And the client is using a higher transmit power in this case, but it has a negative gain on the antenna, which can happen sometimes. And so here you can see that we have roughly the same ERP on both ends, which can help us guarantee the a good synchronous communications between the clients and the APs. In this, what I would pay more attention to is the transmit power, because the gain works in both directions. The 3 dBi gain will be added when the AP transmit its signal, but it will also be added when it's receiving signals from clients. So what's more important is that you have your transmit power that actually matches from the clients and the AP. When we take a look at the different frequency bands, they don't really all have the same RF properties, and that's due to the difference in frequency, right? So you can see in Wi-Fi, we are using 3 frequency band, 2.45 gigahertz, 6 gigahertz. And the difference between these signals is that they they don't have the same wavelength, what we call the wavelength, which is the separation between two cycles. And you can see that the lower frequency signals, we have a wider wavelength than the higher frequency signals. So the frequency and the wavelengths are inversely proportional to one another. So if one goes up, the other one goes down. So what that means for us in Wi-Fi is that 2.4 signals, we have a larger wavelength than 5 gigahertz and 6 gigahertz. And that will impact a couple of things. The first thing that it will impact is the antenna, because we need to, in order to be able to receive a given frequency, we need to design the antenna in a way that it can actually understand that frequency and that wavelength. So the bigger the wavelength, the bigger the antenna will be. So in Wi-Fi, typically we'll have bigger antenna elements for 2.4 than what we have for 5 gigahertz. And the bigger the antenna is, the more energy you can receive on that antenna. So we will tend to receive stronger signals on 2.4 versus 5 gigahertz because we have a bigger antenna and a bigger area to receive that energy on. And that carries over to 6 gigahertz, even though the difference between 5 and 6 gigahertz is not as big as the difference we have between 2.4 and 5 gigahertz. So the size of the antenna will matter here, and it will impact a little bit how much energy we can capture from these frequency signals. And also, when the signal will go through attenuation objects, the more cycles you have going through the attenuation objects, the more attenuations you're going to have, the more absorptions by that element you're going to have. So you may actually, have a little bit more attenuation from a signal that's from a higher frequency, 6 gigahertz, than that you would have from 2.4. So 2.4 would tend to penetrate a little bit better than 6 gigahertz or 5 gigahertz due to the fact that we have less cycle in 2.4 than we have in 6 gigahertz. So that's that's some of the reasons why we tend to see 2.4 traveling further than 5 gigahertz or 6 gigahertz. That's because of these properties. Okay, another thing that I wanted to talk about here is a couple of metrics that are important for us in Wi-Fi. And in Wi-Fi, to express the strength of a signal that we're receiving, we use the RSSI metric, received signal strength indicator, and that gives us how strong the signal is, right? But that's not the only metric that actually matters for us in Wi-Fi. On top of understanding how strong the signal is, we also need to understand the separation between the noise that we would have on a given frequency or given channel and the signal that we're receiving. And the more separation we have between the two, the easier it's going to be for the Wi-Fi devices to decode the message, right? And that separation, this is what we call the SNR, signal to noise ratio. And so the more separation, the better it is for us. And that's going to impact the data rates that we'll be able to maintain on a Wi-Fi connection. So the higher my SNR is, the more separation I have between my noise and my signal, the higher data rates I'm going to be able to support on that connection. So if you want your clients to go as fast as possible, you need to provide them with a good SNR, okay? This slide is nice because it kind of compares what happens if you do not have a good SNR, right? So here we have two devices, it could be the same devices, it could be an iPhone, for instance. The first one is receiving a low signal strength. So if it has a low signal strength, a low RSSI, most likely we will have a low SNR. And if I have a low SNR, then I'll be stuck with using lower data rate. And if I use lower data rate, well, guess what? The connection will be slow for me because I have to use a low data rate. But I'm also going to be using a longer time to send my data on the channel, and that will slow the traffic for everyone else that's also using that channel, right? So it's like a double-edged sword here. It's like, I have a slow connection for me, but I'm also slowing down the connection for everyone else, right? So you could picture a one-lane road here, and then you can picture having like a very old car driving on the road, and they cannot go more than 50 kilometers per hour. And so the car is going slow, but then it's also slowing everyone else that's behind the car that can't pass the car. So if you want to go, and if you're behind that car, you can go faster. All you have to do is wait for that car to be done, to turn left or right before you can start going faster. On the other hand, if you have the same device, but this device has a good signal strength, now we're going to have a good SNR, and we're going to be able to use higher data rates, meaning that, well, the communication will be faster for us, but it will also be faster for other people on the channel because we can free up the channel faster. We can go on and off the channel faster. That will free up, more time, and that will increase what we call the capacity of the channel, the capacity of the Wi-Fi net. So when we design Wi-Fi, usually what we try to do is we try to provide a high SNR to our clients as most as possible. So they can be on and off the channel as fast as possible, and they can have a fast connections on the end. Now, when we talk about Wi-Fi and frequencies, we also have to talk about channels, right? Because we have some regulations that we have to follow, and we have some rules as well, best practices that we have to follow in order to make sure that we're not sabotaging ourselves. When we talk about Wi-Fi, we like to think that outside interference are usually killing Wi-Fi, but most of the time, if we look at most of the Wi-Fi networks we work on, we troubleshoot, we find out that Wi-Fi is sometimes the biggest enemy to Wi-Fi. Right. And sometimes if we don't do it properly, our own Wi-Fi can be our biggest enemy. So understanding the channels, understanding how to configure the channels can prevent you from, creating your own interference and can help you make sure that you're building a better Wi-Fi network. So 2.4 is the first frequency band that we can use in Wi-Fi. The size of the channel that we use in Wi-Fi is 20 megahertz or 22 megahertz, depending on which data rates we use. The modern technology tend to use 20 megahertz wide channels. So if we take a look at the entire frequency band that we have, it means that we can only use 3 non-overlapping channels. And these channels, they're typically 1, 6, and 11. So we use 1, 6, and 11 because that guarantee that we do not have any overlapping between our Wi-Fi channels. And that also guarantee that we play nicely with the other wireless technologies that are now heavily using 2.4 gigahertz. And I'll show you that in a bit. But here I'm talking about BLE for the most part, because BLE is using 2.4 quite a bit, but they work around the 1, 6, and 11 channels. So if you do not want to have any problems or the least problem as possible, you can stick to 1, 6, and 11 on the 2.4 frequency band. What happens if you don't? Well, you could have something called adjacent channel interferences. So in this case, you can see that we're using channel 3, 6, and 9, and we have a little bit of overlap between channel 3 and channel 6, and a little bit between 6 and 9. And what happens here is that if you have, if you have one AP on channel 3, one AP on channel 6, if my 2 APs start talking at the same time, they will actually interfere with one another on that piece of spectrum that they're sharing. So that can, introduce some retransmissions, and that can alter the Wi-Fi communications. Okay, so how to avoid adjacent channel interferences? Easy, just stick to 1, 6, 11. Okay, then you're going to tell me, okay, what if I need to install more than 3 APs, right? Because I only have 1, 6, and 11. What about the 4th AP that I need to install? Which channel do I use? Well, what's going to happen usually is that if you have to install multiple access points, 50, 100, you can end up with multiple access points sharing the same channel. So you could have a case where at one given location, 3 APs are using, channel 6. And what will happen in this case is that it's not really the APs are not really going to interfere with one another. And that's because they are operating on the same channel. So since they're operating on the same channel, if one AP starts communicating, the other APs will actually see these frames and they'll understand that the first one is communicating. So they're not going to try to talk at the same time. They're going to take turn. So it's not really an interference per se. That's why sometimes we call this co-channel contention. But what's going to happen is that all APs sharing the same channel will have to take turn. So they have to share the channel access. And that might decrease the capacity of your Wi-Fi network. Okay.
Hey,
It's
Francois.
very, yeah, go ahead, Matt.
There's been, sorry to interrupt you, there's been some really good questions that come into the Q&A, really relevant to what you're talking about right now. So a few people have asked around channel overlap, could you not use channels 1, 5, 9, and 13, or could you use 2, 7, and 12? And does ACI happen with other APs infringing on another? So maybe you could just answer why you might not want to do the 1, 5, 9, 13 or 2, 7, 12.
Yeah, good questions. Thank you, Matt. Yes, you could. So if you use 20 megahertz wide channels and OFDM data rates only, you could totally, in some countries, use 1, 5, 9, 13 and use 4 channels instead of 3. The main reason why we don't do this today, it's because first, if you use 1, 5, 9, 13 and your neighbors are using 1, 6, 11, and you can hear your neighbors a little bit, then now, you know, my channel 5 is interfering with their channel 6. So you might be interfering and creating adjacent channel interferences with your neighbors. The second reason why, and I would say that's the most important one today, is the reason why we don't use that 1, 5, 9, 13, it's because of BLE. And BLE is using, they have like 40 channels, I believe, but 3 of them are advertising channels that anyone can transmit on. And we have a lot of, we don't really notice it, but we have a lot of BLE devices out there nowadays that will use these advertising channels, including our access points sometimes. And that generates a lot of traffic, which is roughly around channel 4 and roughly around channel 13. So if you use that 1, 5, 9, 13 channel plan, then you're going to have a little bit of BLE that will come and interfere with your Wi-Fi. So that's why usually most of the time we stick with 1, 6, and 11. Because they are the first non-overlapping channels that were defined in that frequency band. That's why we start at 1. Yeah.
Thanks, Francois. And there's just one other thing that people in the chat are insisting that I tell you, and they told me that I have to tell you that you're the best. So there's lots of people in the chat that have been in one of your classes before, or maybe listened to you on your Clear to Send podcast, but they insisted, as I interrupt you here, that I got to let you know that they think you're the best.
Thank you. I appreciate that. Maybe it's the French mafia, you know. Thank you guys. I appreciate that. Okay, so co-channel interference. Yeah, this is going to happen, especially on 2.4. If you've done a little bit of Wi-Fi, you've probably seen it, you've probably measured it, but we're going to have co-channel interference in 2.4. The goal usually is to minimize it as much as possible. And this is something that we can, most of the time, work around on the other frequency band, 5 gigahertz and 6 gigahertz. Why? Well, let's take a look at 5 gigahertz. First thing you notice on 5 gigahertz, I know this might be a little bit overwhelming here, but we have a lot more channels available on 5 gigahertz, right? So I'll take the US as an example. I think in the US they have 25 channels available on 5 gigahertz versus the 3 that you have on 2.4. So, you know, right off the bat, we have a lot more channels available. Another thing that works in our favor on 5 gigahertz is that we have enough separation between our 2 channels to not have any overlapping. So I can use channel 36, I can use channel 40 without any overlap, so without any problems. So I can actually use all of the channels that have been defined on that frequency band. So the ability to have more spectrum, that's good because, you know, that means we don't have to reuse that channel as often, so less co-channel interference. But that also means that we can start innovating. And one of the innovation that came with Wi-Fi was the channel bonding, a feature where it lets you take 2 adjacent channels, bond them together, and then now you have a larger channels. You know, and what would be the advantage of a larger channel? Well, you can transmit more data and you can have higher data rates. So by having more spectrum, we can actually, you know, potentially increase the data rates that we're using on our Wi-Fi networks, which is a great, you know, great benefit of having more spectrum. The thing that we have to keep in mind with 5 gigahertz, though, is that because it's a large spectrum area, we may have different rules that we have to comply with for different subset of that 5 gigahertz bands. That's why you can see that here we have something called Uni 1, Uni 2, Uni 2 extended, Uni 3, Uni 4. And that comes from the regulators the agencies that regulates the frequency space, they actually have it broken down, and they may have different rules because in the past it was used for different purposes. And we have to be aware of this when we deploy network, when we deploy Wi-Fi APs. We have to understand where are we installing these APs, what are the regulations in that country, and let me make sure that I'm not going above what I'm supposed to be doing, I'm allowed to do in those regulations. One thing specific to 5 gigahertz would be something called DFS. You have it on the diagram here, DFS. And DFS stands for dynamic frequency selection. And what happened is, this frequency space, I'm going to take you need to extend it for the US, for instance. This frequency space was actually used, by other devices, wireless devices, before they allow the Wi-Fi people to use it. So once they allow the Wi-Fi people to use it, they told the Wi-Fi guys, you can start using it, but you need to give the old guys the priority if they come back, or if they're using the space, you need to back off. And that's how they came up with the DFS mechanism, which will pretty much, check if the channel is used. If the channel is used, the Wi-Fi devices will not use them. If it's not, the Wi-Fi devices will start using the channels. But then if an old device come and start using that frequency, the Wi-Fi will just say, okay, I see you here, I'm just going to move to another channel. And dynamically, it will just move to another channel, hence the name dynamic frequency selection. So you can see that a lot of channels have to comply with this DFS mechanism. And sometimes, these can have some implications. And we could talk, maybe 2 hours on this subject alone. But here we have like a checklist of things you could do if you ever hesitating on using these channels or not. I know we have this discussion sometimes. But my point of view on this is that it would be a little sad to waste all of these channels just because once in a blue moon you can have activity from an incumbent. It's usually a radar system that will come and then ask the Wi-Fi to move away. So my philosophy on this is more use the DFS channels, but then monitor what's happening on these channels. And that's kind of like what they say here as well too. So use the Wi-Fi channels as long as your client devices support these DFS channels, you're good. Most of the time nowadays, it's pretty good. The support is pretty good. And then, once you've deployed the network, monitor what's going on these channels over the first week, 2 weeks, 1 month, and try to identify if you have any DFS events. So any event where you saw the AP move to another channel because it detected a DFS event. If you had some, great, analyze them, right? Was it on all of the DFS channels? Was it just on channel 100? Is it periodic? Does it come back always, all the time? And then from your analysis, you can just say, okay, I've done my analysis. We've had some DFS channels, but they always happen on channel 100 and 112, whatnot. And so we're just going to decide not to use these channels for Wi-Fi, but we're going to use the other DFS channels. So you can kind of refine your channel planning based on your analysis. So you don't have to necessarily waste all of these channels because of the DFS event. Okay, and then 6 gigahertz. 6 gigahertz is also very exciting because it's a lot more channel spectrum available. That also depends on the country. But if you take the US, for instance, it's 1.2 gigahertz of spectrum available, 1200 megahertz, right? So that's pretty much a little bit more than twice what we have in 5 gigahertz. And that gives us like an additional 59 20 megahertz wide channel. So it's a lot more spectrum. And this is why people have been excited about it. It's because it's more spectrum, which means we should be able to use larger channel width for our channels, which means that we can have higher data rates, faster Wi-Fi communications. And also because it's not as used as 5 and 2.4, we can also expect to get beta latency. So that can enable new sets of applications that we can now use over Wi-Fi. They've been talking a lot about things like augmented reality and use of a Wi-Fi, which is quite interesting. But once again, because this is new and Wi-Fi is new in this space, we also have some rules that we have to follow if we want to be able to generate Wi-Fi in 6 gigahertz. And one of them is the classification of devices. So they created this classification called low power indoor, which are Wi-Fi devices that you're allowed to use indoor under a given transmit power level. And if you comply with this, you can just deploy Wi-Fi as we do today without any additional verifications. But if you want to deploy Wi-Fi outdoor, if you want to deploy 6 gigahertz Wi-Fi with more power indoor, then you need to comply with what they call the SP, the standard power mode. And with the standard power mode, before turning your radio on, you're going to have to comply with something called AFC, Automated Frequency Coordination System. And you'll pretty much have to tell your the AFC provider, which talks directly to the regulator, tell where you are, tell them which channels you want to use, and they come back to you and they tell you you're okay to use it, or these channels are available, these ones are not, and you'll only use what you're allowed to use in that given space. Yeah, so depending on what you want to do, you're gonna have to comply with the regulations and understand that categorization of devices. Now, if we compare 2.4, 5, and 6, here you can really see, the spectrum available on each frequency band. On 2.4, you can see we have 80 megahertz, so 3 channels. On 5 gigahertz, roughly 500 megahertz, which gives us 25 channels about. And on 6 gigahertz, we now have 1200 megahertz, which gives you 59 channels, right? And that, once again, not every country has access to everything. Every country would have their own regulations. For 6 gigahertz, I know that in Europe right now, they only have access to the Uni 5, which is pretty much 500 megahertz. So it's like getting another 5 gigahertz. I believe it's 24 channels. But you can see that they're trying to push access to more spectrum so we can actually increase some of the data rates we're using over Wi-Fi. Okay, so a couple of other things as well that I wanted to talk about here is what happens to the signal when you actually when the signal leaves the access points of the transmitter and is being transmitted in your environment. One aspect of Wi-Fi that is important to understand, especially when we work with Ekahau, is what we call the free space path loss. And this is pretty much a formula that calculates the loss of the signal as it's leaving the transmitter. So if you take an AP, the AP is transmitting a signal, you can actually calculate that natural attenuation of the signal as it's leaving the transmitter, right? And here you can see some of the calculations. But the takeaway from here is, the closer you are from the transmitter, the more loss you're going to have. And then the more you're going to step away from the AP, the less loss you're going to have. It's not a linear loss, it's more a log loss. And you can see here that in 2.4, in just the first meter, so 1 meter away from the AP, you're already losing 40 dB, which means that you only have 1/10,000th of the original power 1 meter away from the AP. So you have quite a bit of loss at the beginning, and then less as you move away from the AP. Since this is a calculation, you can, software like Ekahau can take this and model this for us. That's actually what Ekahau does. But this doesn't take walls into account. This is a free space. So if you have wall attenuations and so on, you have to model it in Ekahau. So Ekahau can take the free space path loss and the wall attenuation into account to model the environment for us. So this is what you have here, right? If you have a wall, and we're going to draw the wall in Ekahau, Ekahau will calculate the free space path loss before the wall, add some loss to it, and then free space path loss after the wall to model the environment. And it does it in 3 dimensions. So you can actually look at how the signal is transmitting on a horizontal plane, but also on the vertical plane. Other things that we could also model are reflections. So what's going to happen to the signal is, some of that signal, some of that energy might bounce against some surface that are a little bit more opaque, and some material will bring more reflection than others. But some of that energy might come back into a given space. And in Wi-Fi, we usually talk about metal, and then we say that metal is creating reflections, reflecting the signal, and sometimes we could have the signal bouncing around, which makes it a little harder for the receiver to actually decode what's going on. But we can also think about reflections by other material. If you work a lot in warehouses or manufacturing plants and they have big concrete floors, that could also reflect the signal, or concrete wall that could reflect the signal a little bit. And sometimes you can see it when you measure it in Ekahau. So you can take that into account when you're doing your survey, when you're measuring the signals. But also this can also be taken into account in the modeling in Ekahau. Diffraction also is happening, and diffraction means that the signal will, is bending around an object, it's going around an object. And in Wi-Fi, this is usually, what will happen if you designing in a space, in an open space that has pillars. So let's say you have concrete pillars in an open working space, then the signal will bend around those concrete pillars. And this can also get modeled in Ekahau. And this is nice because it allows you to have a better representation of what the signal will be in the real world from the modulation. So the reflection diffraction can be used by Ekahau to give you a simulation that's closer to the reality. So here you have an example of the pillars being modeled. On the left, you can see that the diffraction model is not applied. So you can see that there's like some sort of a V-shaped shade area that's created behind the pillar. But then if you enable the modeling of the diffraction, you can see that the signal is actually going around that pillar. So as long as you don't place the AP too close to the pillar and you leave some room for the RF to breathe, then you shouldn't have to worry too much about that pillar. Why don't we take a look at it in Ekahau? Sounds good? Okay.
Sounds very good.
Okay, so what we'll do is I'll show it to you in Ekahau AI Pro Online. But I'm going to start from Ekahau AI Pro so I can show you the new feature of importing an existing project into the new online platform. So I'm going to jump into Ekahau. Matt, do you see my screen? Awesome. Okay. So this is pretty much Ekahau. If you guys have never seen Ekahau, this is what it looks like when you open it. And I'm going to use the design tab because I'm just going to do a quick design here. And the first step in the design is to add the floor plan. So I can click on add, and I have the floor plan ready here on my desktop. And so this is the Ekahau offices in Finland. I have imported the image, and now I have to scale it. Ekahau is kind of guiding you a little bit because the scaling tool is the only one you have available here. I have a scale here on the image, which is convenient. So I'm just going to use that to scale to 10 meters. And then once my floor plan is scaled, then now I can start, kind of modeling the environment. I'm actually going to let the online tool model the environment because it can do it automatically. But what I'm going to do here is I'm going to define the areas, the requirements areas, and the coverage areas. So I'm going to go in the area tool, and I'm going to define an area for the offices. And here, Ekahau, they're not using the entire floor for the offices. So I'm just going to go around the building here, selecting this area. And then you notice at the top here, I can assign a profile. And this is what we call the requirement profile. So I can choose, pretty much which level of Wi-Fi I want to have in this area. I'm just going to use the best practice for now, and I'll show you what that means in the online tool. And then what I'm going to do is I'm going to also configure the exclusion area. So now I'm going to exclude here the staircase here, and I'm going to exclude an area here with the elevators. So this is the exciting part of the webinar. You just watch me click. Okay, and then once I have this, what I'll do, I won't do too much more here. I'm going to save it. And I'm going to save it in the cloud. And I'm just going to call it webinar 2025. And what this will do is it will just take my project, upload it to the cloud. And this is good. And so now I can go back into my browser, and I can go into my Ekahau Cloud account. And here I can go on the Ekahau AI Pro online tool. It will show me my project here, but I'm actually going to click on create a new project. And this is where you have the new feature for today, where it's asking you if you want to import from an existing project, from an AI Pro project. So I'm going to say yes. Maybe I should give it a name here. Okay. I can choose the regulatory domain. I can choose the site, and then I'm going to continue here. And it's going to show me all of my projects. I'm going to select the one that I've just uploaded. And here, what it will do is it will kind of import the floor plan, the scale, the areas, pretty much anything I've done in Ekahau, and it will put it here into Ekahau AI Pro Online. And you can also notice that it's detecting the walls for me. So now it's running an algorithm to detect the walls from the image. It takes about 15 seconds, and then it will allow me to place the walls automatically, so I don't have to draw everything. And you can see that they have different profiles of different walls with different attenuations already exist already. And so here I can click on place walls, and it will just place the walls for me. So I can kind of see what it looks like. If I'm not happy with different areas, I can adjust it. Here I noticed that they added walls for the legend, so I can actually delete them. And then if you want to go fancy, you can go 3D, right? And you can take a look, right, at what the walls are. It's pretty good, actually. And especially that I didn't have to draw the walls, right? So it's even better. Okay, and then here you can also see that we have our areas. So if I take my area here, I have this area, and it goes back to my area requirements profile, and I can take a look at what this means. And you can see that here for each frequency band, we're going to have minimum thresholds being set to meet some of the Wi-Fi design requirements, to make sure that we have enough signal, secondary signal, SNR everywhere, to make sure we have good Wi-Fi. So this is great. Okay, so now what if I place an AP? I'm going to go to the device tool, and I'm going to place an AP. So I'm going to go and get Wi-Fi 7 AP. I'm doing design right now with this one, so I'll grab this one, and then I'll place it. I'll place one here, and you can see that as soon as I place it, it calculates the signal propagation from that AP. So how does it calculate this? Well, it uses the free space path loss. How do I know it uses the free space path loss? Well, I can actually, I can put my cursor in any area, and at the bottom it shows me the signal strength in dBm. But what I can also do is, if I put my cursor on the scale at the bottom, you can see that it kind of colors the heat map and shows me which areas that I have in this case that provide the signal greater than neg 54. And you can see each increment is an increment of 3 dB. And you can see that we also have little contour lines, right? And so here, if I look at my legend, we actually have 6 dB difference between my contour lines. This one is at neg 54, and this one is at neg 48, 6 dB. And the FSPL calculation is telling us that every time you lose 6 dB, right, you double the distance away from the source. So here, it kind of illustrate that. You can see the distance between the AP and that contour line doubles when I go to that contour lines. And this means that I'm losing 6 dB in the process. So Ekahau is using the free space path loss to calculate the signal propagation. But then if I go close to a wall, you can see that the wall, I have to sign in again. Sorry about that.
We're nice and secure. Clearly, you've been working for too long today, Francois.
Yeah.
We'll make sure no
I guess
one...
it's started my idea too early, I guess. Okay. So when I go to a wall, you can see that it's going to be a little bit more than the free space path loss, because now it's adding the attenuation of the wall. But then what if I what if I zoom in on a pillar and we start looking at this? and we start modeling the pillar, then maybe we can illustrate what the diffraction model will do. So I'm going to take a wall, concrete wall, and then I'm going to, you know, really quickly here define a wall around my pillar. Okay, and then if I go back up, so here you can see that, I don't know if you saw it, but if I move my AP, you can see that I can see the big V shape because the diffraction model hasn't applied yet. But then as soon as I release my cursor or my finger on the mouse, then it calculates that diffraction model. So you can kind of see, and maybe I can zoom out to illustrate that a little bit better. You can see the impact of that pillar without the diffraction and then with the diffraction. So you can see that there's not much impact when you have the diffraction, unless I place the AP like really close to the pillar, and then you have a little less signals, obviously, coming on the other side of that pillar. So usually for the pillars, what I do is I give, you know, my APs a little bit of a breathing rooms around the pillars to try not to install the pillars too close, the APs too close to the pillars. And then if you have pillars like this, I try to install APs on both ends of the pillars, so at least you have good coverage. And if you do have to install the APs on the pillar, well, now you know the implications and you can model them. Okay, and then here, I know I'm talking a lot, but here what I could do in this environment is I could actually go back to my device tool and I could place more APs. And you can see how Ekahau is guiding me into where I could place more AP if I want to meet my requirements. So here I clicked manually, but I could actually ask Ekahau to place my APs automatically, and it will give me a design that meets my requirements. And then if I'm curious, I could always go back and look at 6 gigahertz. What's the secondary signal strength? What if I add an AP here? And then I can, you know, continue doing my design that way, making sure I'm meeting all of the requirements. And then if I want to understand my channels, then, you know, in Ekahau AI Pro, I could go first on the left and understand based on my regulatory domain, am I using the channels that I'm supposed to be using? Here you can see that I have a little red dot. And if I click on the red dot, it's telling me that I'm actually using channels that I'm not supposed to use in Finland. So here I would have to disable Uni 6, 7, and 8 to be able to comply with my regulations. So I can pick and choose for, you know, all of the frequency band, which channels I want to use, which one I don't want to use. And then if I go back and take a look at my network devices, I can take a look at which channels have been assigned to my APs, and you can see that Ekahau automatically assigned the channels. I can actually display them on the map here. It automatically assigned the channels and try to optimize for co-channel interference, and I can study that here on this slide.
Hey, Francois, I'm just going to steal the share quickly because I want to talk people through how they can win an ECSE design seat. And I know people will have to drop now because they've got another call coming up. So let me just quickly jump to here. So to enter to win an ECSE design seat, and you may even be in a class with Francois, getting taught by Francois in the future. So all you need to do to enter to win is either go to Twitter or X or LinkedIn and let us know why attending an ECSE class is going to help you further your career. Also, make sure that you tag Ekahau and then also use the hashtag ECSE, and we will go through all of your posts and we will pick a random winner and we will contact you about how you can claim your ECSE design seat. And you never know, you might even have Francois. And if you enjoyed today's webinar, you can register for our next upcoming webinar, which is going to be with Cisco all around Wi-Fi 7. And we are going to be having the core members of the team that have set up, managed, and deployed the Wi-Fi network for Cisco Live in Amsterdam. So they're going to be talking us through all of the challenges that comes with a large public venue that's holding thousands and thousands and thousands of people with client devices. And I heard that they're going to be deploying some Wi-Fi 7 there. So that's going to be a really interesting webinar to get some great insight into how you can deploy and manage such a large enterprise Wi-Fi network, and especially around Wi-Fi 7. So thank you for attending the webinar today. So thank you, Stu, Dale, Jacob, Francois, and all the rest of the Ekahau marketing team, and everyone for joining us on the webinar today. We look forward to hopefully seeing you at some of the industry events over the next couple of weeks. But if not, we will see you on February 20th for the next webinar. Have a great rest of your day and look forward to seeing you soon.
Thank you. Thank you, guys.